Hello and welcome back to the class. So today we will be learning about particle in a 1D box. So the topic particle in a 1D box comes under quantum mechanics. So the first thing that comes in our mind is why we need quantum mechanics. So basically the means the failure of we can say the failure of classical mechanics and the classical mechanics was not able to solve the properties, or it was not able to find the values related to microscopic particles like electrons, protons, atoms, molecules, and so we were forced to make quantum mechanics. So basically, suppose if we want to study an object like a moving car, so we can find out the velocity, we can find the mass of the car, we can find the force or the torque applied. We can easily calculate by using the classical mechanics. So in classical mechanics we have Newton's equation. So what is Newton's equation? So Newton's equation is F is equals to m into acceleration. So force is mass into acceleration. So I can calculate the acceleration if I know the mass and force, and I can also calculate the velocity of the car. So to calculate the velocity of the car, we know that acceleration is nothing but it is change in velocity with respect to time. So I can calculate this velocity if I know this time, if I know this mass of the object, and if I know the force of the object. So I can easily calculate the velocity. I can just find out any property, any value or any property of the object I can find. But this comes under classical mechanics. But when we try to study the same properties related to electrons, protons, which are very, very small particles, and the size of these electrons and protons comes in the nanometer range, that is 10 raised to minus 9 meters. Okay, 10 raised to minus 9 meters. So it is very, very smaller, and these particles behave somewhat like waves, and these particles cannot be studied using the Newton's formula, that is F is equals to mass into acceleration. So in the Newton's theory we have also studied that every body will be stay in rest at a constant velocity until it is disturbed. Okay, so this is the first Newton's first law. Then in the Newton's second law, what we studied that acceleration of an object is directly proportional to the force and inversely proportional to the mass of the object. And in the third law, as we all know, that we have studied that every action has equal and opposite reaction. So all these theories were not able to we were not able to apply on the microscopic particles like electrons, protons, atoms and molecules. So in order to study this, we have to make a new theory or new subject called as quantum mechanics. Okay, so that is how we try to make quantum mechanics, so as to study the properties of these microscopic particles. So now, as we have Newton's equation in classical mechanics, the same way we have Newton's equation in quantum mechanics as well. Now the Newton's equation of quantum mechanics is called as Schrödinger equation. Okay, so it is somewhat called as Schrödinger equation. So the Schrödinger equation says that if you want to study any system or an electron and a proton or a particle in a box, it can be 1D box, 2D box or 3D box. So what we can do, we will first take an operator. Okay, an operator, then we will have a wave function of the wave function will define the behavior or the property of the system, of the particle or the system, that is microscopic size, and this will be equals to a constant value E and multiplied by the wave function. So this is what is given by Schrödinger equation using this. So this is nothing but the Newton's equation in quantum mechanics. And so now what is this? This is called as operator. It is like doing mathematics. Like we have addition, subtraction, then we have division, then we have differentiation, then we have integration, and all those mathematical operators we have. So same thing we have here also in quantum mechanics. Also we have some operators. We will apply the operator on the wave function, and we will solve, we will do some mathematics, and we will get a constant value multiplied by the wave function. Okay, so what is this wave function? This wave function is nothing but it will be called as expression in the terms of x, y or z. In the terms of x, y and z, this will be an expression. So now since we are dealing with one-dimensional box, so one-dimensional box will be having only one variable, that is x, and two-dimensional box will have say two variables x and y, and three-dimension will have three variables, say x, y and z. So like this there will be variables depending on, and using these variables we will be making some expressions that will somewhat tell about the behavior of the particle, and then we will apply some mathematics or operators on this wave function. We will do some mathematics, and then we will get a constant value multiplied by this wave function. So this is what we try to do in quantum mechanics, to study these particles which are very small in size and they have some wave-like properties. So using these values we can find out the momentum, we can find out velocity, we can find out mass, we can find out energy, we can find out the energy levels, how they are arranged. All this we can find out using this Schrödinger equation. So now our today's example is particle in a 1D box. So if I explain you, so what happens in a, now suppose we have a box. Now this is, now we all know that this is a 3-dimensional box, okay, and then this is a 2-dimensional box. And how will be a 1-dimensional box? So 1-dimensional box will be like this, okay. So you have to consider that now see in 3-dimensional box there will be how many axes? 1 axis, 2 axis and 3 axis. So total 3 axes are there. Here also we have x axis and y axis. Here also we have only one axis, the other axis is absent. How? Like we can neglect the quantity 2 in comparison to 1000. Okay, so we can easily neglect this quantity. So same thing we are doing here. The length of this wall is so high, or we can say infinity, that as compared to this length is so smaller, and so our system becomes 1-dimensional system. So now we have a 1-dimensional box. Now in this 1-dimensional box, suppose we have a 1-dimensional box like this, and the particle is moving inside this 1-dimensional box. And so let us consider this is the length 0, and from 0 at a distance x, this is the length L. Okay, so now the particle is moving inside this, and now this particle can move from one place to another. So what we will consider that here the potential is very high, and here also the potential is very high. So the particle cannot move out of this box, or out of this box it cannot move out of the box, and so the particle will remain inside. Now suppose I want to calculate, for example, the energy of this particle. So what I will do, first thing I will do is I will consider Schrödinger equation, H psi is equals to E psi. Okay, so now what is energy? Since I want to calculate the total energy, so total energy is nothing but kinetic energy plus potential energy. So kinetic energy plus potential energy will give me the total energy. So now in quantum mechanics, kinetic energy is given by a value or an operator. So what is that operator? That operator is nothing but h bar square upon 2m, and potential energy is given by V. Okay, so now since we have considered that the potential energy of this particle is near to 0, why we have considered this as near to 0? Because the particle should not escape out of this box. So the potential of this particle is considered as 0, and so there will be no potential energy. That means potential energy is equal to 0. So our total energy becomes kinetic energy, which is nothing but minus h bar square upon 2m. Now what is this h bar? This h bar is nothing but Planck's constant. We all must be knowing Planck's constant. So this is called as reduced to Planck constant. So just remember this h is nothing but h upon 2 pi. Okay. Now what we will do? We will apply this operator as a mathematical function on this equation, and we will try to find out the energy of this system. So what we will do, in the place of h operator we will apply this mathematical operator. So what is this h square upon 2m multiplied by psi into, so here as we already considered that v of x with respect to psi x and e psi x. So here, as I already told you, that this potential energy term is becoming 0. Okay, why? The potential energy of the particle should be 0 so that it cannot escape and move out. And here you see the potential is infinity. So as compared to this value is very smaller, and that is why the particle stays inside the box. Now since this term is gone now, so we are remaining by this term. So what we will do? We will solve this. So when we solve this, so we get some solution of this. Now see, one thing I have to say, so it will become as double differentiation. Okay, so this will be a double differentiation. So here also it will be a double differentiation. Okay, so now what I will do, I will just bring this constant term this side. So this will become d square psi of x upon dx square will become minus e upon 2m h square into psi x. Okay, so this is the expression I am getting. Now if you carefully see this, this looks like a double differentiation. Okay, d square means double differentiation. So whenever we solve a double differentiation, we want the expression in terms of the double differentiation. So what we will do, we will consider this constant term as kx. Okay, k square. We will consider this constant term as k square, and this will be nothing but E2m upon h square. Okay, we will not consider this minus. Okay, why we will not consider this minus? So as to maintain the uniformity, or to maintain the uniformity, or we can say that the means it should take a form of a mathematical expression. Okay, so that is why we are not taking this minus with this side. So now what we will get is d square psi of x dx square will become kx k square psi of x. So now you can see we have a expression in the term of a double means you can say it is a second derivative, and that's why this second derivative will be matching with the square of this equation, and this is the expression we were interested. Now mathematically when we solve this expression, what we find is, now this is nothing but double differentiation. So all those who, if you know the double differentiation, you can easily solve this equation. So but in quantum mechanics, when we solve this expression, what we get finally is we get a solution which is called as psi of x is equals to a cos of kx plus b sin of kx. So this is the expression we will be getting after solving this double differentiation equation. So this is nothing but mathematics. When we solve this expression using double differentiation, we should get this solution. So this is our final solution of our system. Now we have to solve this more and more. So we have to make it more and more simplified. We need to find out the value of a. We need to find the value of b. So and this equation I will name is equation number 1. So now what we will do, now since we have considered that the boundary condition, that means the starting point is 0 and the last point is L. So the value of x can be either 0 or L. And here we have also considered that the particle cannot move out of the box. So that means the position will be, so the value of x will be not lesser than 0, right? It should be not lesser than 0, and also it should not be equal to 0. Why it should not be equal to 0? So it is said that the particle is having a form of a wave function, means it is having a wave nature, and that wave function should be continuous. Okay, it should be not discontinuous. Okay, so that is why the particle cannot stay at the borders as well, means it cannot stay at the boundary as well, and that is why the value of x cannot be equal to 0. So if the value of x is less than 0 or equal to 0, the value of wave function will become 0. So this is what we have got. The value of wave function will become 0. Again, if the value of x is greater or equal to 0, again the value of psi will become 0. The value of psi x. Okay, so this psi x will become 0 if the particle tries to move outside, or this side, outside of the box. So the wave function will not exist, and that is why we. So this is nothing but called as the boundary condition. Okay, so now we will be using this boundary condition. So first we will consider that suppose x is 0. So now what we will do, we will apply this boundary condition, that is first we will apply x value as 0 and then we will apply x value as L. Okay, so this will be L. So now first we will apply psi x as 0. So when x value becomes 0, what we will get is a into cos. Now see, x value will be put as 0, so 0 into k will be 0, so we will get cos 0. Now we all know what is the value of cos 0 plus b sin. Now sin 0 is 0. Okay, so sin 0 is 0. So what I will do, I will just remove this because this whole term will become 0. Now cos 0 is 1. Now this psi of 0 we already defined the boundary condition that psi of 0 is always 0. At boundary, psi of 0 will be 0, means wave function will be 0. So this will become 0 is equals to a into 1. So now we have got the value of a. A is nothing but 0. Okay, so this is what we have got. The a value is 0. How we got this? Because the sign 0 is 0. Now this was the first thing we did. So this we can say as equation number 2. Then the second, what we will do, we will put x value as L. So psi of L, what is psi of L? Psi of L is also 0. So this will become a. So psi of L is also 0. This will define that psi of L will also be 0, means at this wall, at this boundary also the wave function will not exist. So psi of L will be cos kl plus b sin of kl. Okay, so sin of kl. Now here we got the value of a. The value of a is nothing but 0. So this term will become 0. 0 into anything will be 0. So what we got? B sin k L. So 0 will be equals to, so psi at L will become 0 when B sin is k into L. Now this is what we are getting. So again we have to solve this. Now see, what does this indicates? That the sine of B is 0. So yes, so sine of B into sine value will become 0. So when does this value becomes 0? This we have to find out. So here what we will do again. So now we know that now see, this B also I can bring here. Okay, so this will become 0. So this B is a constant into anything will be 0. So this now we have to define that when and where the value of sine will be 0. So that means this is nothing but the theta. Okay, this is nothing but the theta value. So the theta value of for sine should when it can be 0. So it will be 0 when whenever the theta value is either n multiple of n pi. Okay, so what is n? N is nothing but 0, 1, 2, 3. Okay, so n value should be either 0, 1, 2, 3, 4. So when you put 0, so sine of 0 will also be 0. And when you put 1, sine of 180 degree will also be 0. That means, suppose this is your wave function. So when it is moving like this, so this is your 0, this is your pi by 2, and this is your pi. Okay, then this is your 3 pi by 2, and this is your 4. This is your 2 pi. Okay, so this is your 2 pi. So that means only at these positions, only at these nodes, the value of wave function will become 0. Okay, and the value of sine theta will also become 0. So that means that your k into L value, theta value should be either be equal to n pi. So this is what we get from here. Okay, so k into L will be equals to n into pi. So this is what we are getting. Now since we know that k into L is equals to n into pi, so now what we will do, this is k, again we will make this n pi upon L. Okay, this will become n pi upon L. Now since this is the equation we are getting, so again I will name this as equation number 3. So when I equate equation number 3 and equation number 1, what I get is I have k here as well, I have k here as well. So what I can do, I can equate them. So before equating, what I will do, I will just remove this square and I will put this root here. And so when I put the root here, so this 2 is also removed. So means that square root and the square both are cancelled out. Okay. So now what I can do, I can equate equation number 3 and 1. So when I equate equation number 3 and 1, so what I will get, n pi upon L is equals to under root of E to m upon h. So this is what I am getting. So what I will do, again I will square on both sides because I am interested in finding the value of E. So what I will do, I will square it. So this will become n square pi square upon L square. This will also become E into 2m upon h square. Okay, so this is what I am getting. Now after the final step, we will get the value of our pi. So after the final step, so once we rearrange this, what we will get is n square n square pi square upon L square will be equals to, now here I will keep the E here, 2m I can bring here, and h cut square I can bring here. So this is the equation I am getting. Now see, h cut I already told that h bar or h cut is nothing but h upon 2 pi. So what I will do, I will put here h upon 2 pi. So this will be square. Okay. So this will become square. So now 2 ka square is 4, 4 2 is 8 pi square. So this will become 8 pi square into m into m into L square. In the numerator what we will have s square, n square and pi square. Now see, this pi square and pi square will get cancelled out. So we will finally get the expression or the formula of our energy of our particle in this one dimensional box. So now we have got the value of E, that is nothing but the energy, total energy of the particle in the one dimensional box. Since we were interested in finding the total energy of the particle in our one dimensional box, so the final equation is n square h square upon 8 m L square. So this is the expression we are getting after solving the system of one-dimensional box. That means if we have a particle in this one-dimensional box, and if we define the boundary conditions, and after solving the expressions and the differential equation and finding out then equating the k values. So equation 3 and 1, what we get is we get the value of the total energy E. So the total energy of the system is nothing but n square L square upon 8 ml square. So using this energy expression we can find out the various energy levels. Means what is this n here? This n here is nothing but 0, 1, 2, 3, 4, 5, 6 like this. All the energy levels we can define. We can find out all the energy levels. Then we can this h is nothing but the Planck's constant. Then this m is the mass of the particle and L is the length of this box, or this is the L distance. Okay, so using this we can easily find out, and we can easily find out the other parameters as well. So in this case we have find out the total energy of this particle in the box when the potential on the outside is infinity, and once we have defined the boundary conditions. Okay, so this was about the one-dimensional system. Then further in the further class we can find out the momentum, we can find out the velocity, then we can find out the different energy levels, how they are defined, whether they are continuous or discrete, that we can define, and why they are means discrete, why they are means the different energy levels we have. Then we have 0 point energy. This all we can easily calculate for this one-dimensional box, and we can try to study the system and try to find out the properties. Okay, so that's it for today's session. Thank you.